Well, first of all, I'd like to thank the organisers, first of all, for putting together this wonderful program, and secondly, for giving me the opportunity to talk. And I guess my talk will be a talk that maybe people have heard before, in the sense it's a sort of a reworked version of something I was doing some years ago. But I guess what I'd like to do is start off by sort of setting the scene for some of the people who may not have seen the basic questions. So what I'd like to do is in the first part of the talk about the topology of minimal surfaces in hyperbolic three-manifolds. So what do we know, what do we expect to be true for minimal surfaces to look like? The second part of my talk is I want to talk about the particular aspects of hyperbolic geometry, and particularly how short geodesics can be used to sort of understand some of the connections between minimal surfaces and the hyperbolic geometry. I think this is a really interesting area, even though we've known for more than 30 years via Thurston that generically three-manifolds are hyperbolic. We still have, it's extremely interesting, given a three-manifold, what does its hyperbolic structure actually look like? And minimal surfaces are a key tool which should be useful in this plan. And then I want to talk a little bit about normal surfaces, which is sort of something I've been very interested in. So these are sort of discrete analogues of minimal surfaces, and how hopefully there should be more of a connection between normal surfaces and minimal surfaces. Then I'll mention a couple of problems at the end, so sort of rush along a little bit here. Okay, so in the sort of early days of three-manifold topology, I guess showing my age here a little bit, minimal surfaces really played a very, very important role. And this was via the study of essential surfaces. So I'll give the definition of an essential surface in a minute, but there's sort of basic technology which tells us that if you have an essential surface in a three-manifold, you can homotop or isotop it to be minimal, in fact, least area in its homotopy or isotopy class. So this gives us a rich source of interesting examples. However, it's not so easy to say exactly what the minimal surface looks like, and there will be some beautiful talks later in this conference on that particular topic. Okay, so what's an essential surface? So I'm going to focus just on closed orientable surfaces embedded in closed or finite volume orientable three-manifolds. And of course, as in the title of the conference, we're going to assume that our manifolds have hyperbolic metrics. So the essential condition says that the map from the surface to the three-manifold induces a one-to-one map on fundamental groups. So this is the analog of an essential loop on a surface. So this is the way to think about these surfaces. So they tell us a lot about the topology of the three-manifold. Okay, the other class of surfaces which come up a lot, both in the topology of three-manifolds and in minimal surface theory, are Heegard surfaces or Heegard splittings. So in this case, we split our manifold into two simple objects, either handle bodies or compression bodies. So let me just quickly draw for you compression body if you haven't seen it before. So a handle body just looks like the solid region bounded by a surface in R3 in this sort of standard picture. So the idea is you can think of it as a neighborhood of a graph. So it just retracts onto a graph. So this is a handle body. To make this into a compression body, we just want to drill something out. And in particular, in this case, what we're interested in doing is drilling out some cores of the handles. So we may drill out a circle, which is a core of this handle over here, and so what we get is something which looks like this, and that's called the compression body. So the two situations arise because we're interested in closed manifolds, in which case we don't want to drill anything out, or if we have a manifold with tori boundary like a knot space, then we want to drill out some knots, and that's what the knot looks like in the manifold. So you just get these standard pieces on either side of the Heegard surface. Okay, so a long time ago, Pitts and I gave a method based on beautiful thesis of a student of Leon Simon to isotope a Heegard surface to a minimal surface. Okay, so what the idea is that we need a very special sort of Heegard surface to do this, and these Heegard surfaces had been introduced by Casson and Gordon, the so-called strongly irreducible Heegard surfaces. Somehow they're the closest things to essential surfaces. They're the nicest Heegard splittings. So these satisfy a very strong condition that if you look at a compressing disk, so here's a compressing disk for my Heegard surface, and the other side of it might be a handle body, for example. This is a knot space, and then we have lots of compressing disks on this side, etc. And all of these compressing disks on this side must meet all of the compressing disks on the other side. So this is a remarkable property, and it's rather surprising that these splittings are very common. So there are a lot of them. In fact, Dave Gabai is going to talk about using minimal surface theory to enumerate these splittings. So there's a strong connection between these splittings and minimal surfaces. Okay, now there's another class of Heegard splittings that are very important, which are irreducible Heegard splittings, and as the names indicate, irreducible is weaker than strongly irreducible. So these ones are easier to somehow think about. Any minimal genus splitting of a three-manifold, of a hyperbolic three-manifold is irreducible. So minimal genus are always irreducible, for example. So these have the property that there are no trivial handles. So a trivial handle is a pair of compressing disks which meet in a single point. Okay, so what we can do to see what a trivial handle looks like, we could take a splitting like this and we can do an operation called stabilization, which means that we can drill a little tunnel out of this handle body, but an unknotted tunnel, so there's no knot tied in it, and then we can attach that tube to this Heegard splitting. So we remove the interior of this tube and attach it to that one. And so this process is called stabilization, and you can see a pair of disks. There's one disk like this, which is really this disk, and another disk going around the tube which meet in a single point. So if we have such a simple situation, then the splitting is not irreducible, and we can reverse the process and remove that extra tube. Okay, so this is sort of a basic operation in Heegard splittings. Okay, so stabilized Heegard splittings, given any Heegard splitting, we can do this as many times as we like and produce high genus Heegard splittings called stabilized ones. Okay, so then there's an interesting question, which I'll give in a minute, about the connection of this operation to minimal surface theory. Okay, so let me just indicate just a very quick argument to show how simple properties in hyperbolic geometry can give us information about Heegard splittings. So this is a very straightforward argument. So what I claim is that you can find simple examples of nice hyperbolic three-manifolds where the minimal genus splitting cannot be isotoped to be minimal, to be a minimal surface. So this is a little unfortunate, but it shows the subtlety of the subject. Okay, so here's the idea, is that we just take a surface bundle over a circle. Okay, so we just take a product of a surface and an interval, and then we glue the ends by some sort of diffeomorphism of the surface. Okay, so if we have a simple three-manifold like this, if the distance around the bundle, so this distance in the hyperbolic metric is large, what we can prove is that the simplest possible Heegard splitting, the minimal, what's usually the minimal genus guy, can't be represented by a minimal surface. So the argument is as follows, that it's just an area bound. So there's a standard area bound, which I won't write down the argument for, but very straightforward. If you have a minimal surface in a hyperbolic three-manifold, the area is bounded above by minus 2 pi times the Euler characteristic. Okay, and so the argument is really just the second fundamental form, the principal curvatures have to add up to 0, and then you just look at the Gauss equation and this just falls out from Gauss-Bonnet. So it's a very simple argument. Okay, so if we take the standard Heegard splitting of a bundle, which I won't draw, then that has genus linear in the genus of the fibre. But if the distance is very large, if you had a low genus surface like this, which was minimal, it would have to have too large area. And the argument is just monotonicity for minimal surfaces. We know the growth of area in a ball grows exponentially. And so what we can show is that if there's a sort of a long tube in this minimal surface, that has to have large area. If there's a long annulus, it also has to have large area. Okay, so by bound on the injectivity radius. So either way, we can show that minimal surfaces have to have too large area, and so therefore you can't get this.
How do you know that they are arbitrarily long?
Oh, sorry, this is an assumption. It's not so if I have a bundle of this type, and this will come up again. So of course, bundles don't have to look like this. The distance around the bundle might be short, then this argument doesn't apply.
How do you know there exist bundles?
Oh, right. Oh, that's a very easy argument. You can just take a cyclic cover. So just take any bundle, take a large cyclic cover of it. Yeah. Okay, so just to sort of wrap up this introductory discussion about topology, there's a general process to relate irreducible splittings to strongly irreducible ones due to Charlemagne and Thompson. So there's a method of cutting up an irreducible splitting into pieces, and the pieces are in fact either essential or strongly irreducible. It's a very beautiful result, and so what we can see is all the pieces are minimal. So what this means is that the right way of thinking about irreducible Heegard splittings is, from a minimal surface viewpoint, is via Charlemagne-Thompson theory. Okay, so this gives us a very big class of examples of minimal surfaces. So then it raises the following question, well, several questions. First of all, we've shown that if a minimal genus splitting may not be minimal, it may not be a minimal surface, but suppose that there is a Heegard splitting which can be represented by a minimal surface. If you stabilize it, is there a new minimal surface of that type? So that would already give infinitely many interesting minimal surfaces of higher and higher genus in our three-manifold. And just to give sort of one suggestion of maybe a weaker version of this, we don't even know, as far as I know, that hyperbolic three-manifolds have infinitely many minimal surfaces isotopic to Heegard splittings. So suggestion for doing this, of course, there's the technique of Nick Capolaeus of resolving intersections of minimal surfaces by putting tubes in, and that might be a good way of proving something like this, but I don't know how to do it in every hyperbolic three-manifold. But I think these are sort of interesting questions to have a look at. Okay, so here's just a sort of a general summary of where we're at, or a very brief discussion. In all the other Thurston geometries, we really understand the topology of minimal surfaces. So we can say what they look like. Basically, they're either essential surfaces or they're Heegard splittings in the sense of Schalem-Thompson. Okay, so, but in the hyperbolic case, we don't know what they look like. So I don't even have a good conjecture to say what a minimal surface looks like. So I think this is a really interesting question. But just to throw up something to talk about is for some hyperbolic three-manifolds, in particular the ones with very large injectivity radius, it's possible that the only minimal surfaces might be essential or Heegard. I don't know, but I think that's not a ridiculous idea. It's worth thinking about. Okay, so I want to just very briefly, and hopefully I won't hash this up since Jeff's in the front here. So a very interesting model that's been proposed by Brock, Minsky, Namazi, and Souto, which I think Jeff's talking about later. So I want to just give a very brief version of this, and again related to minimal surface theory, and it's slightly related also to this example as well. So roughly speaking, I hope this is a reasonable approximation, the way to think of it is that if you rescale the metric or look at the manifold from a long distance away, all the points are bounded distance away from a graph, and the edges of the graph are relatively long. So the manifold sort of looks like a neighbourhood of some graph which might be quite complicated, might be a tree or it might have cycles, but the points are not far from these long edges. So for example, if we have a bundle where the distance around the bundle is long, the graph is just a circle. So we can think of it as looking roughly like a circle. So the idea is, so here's a suggestion again of a connection with minimal surface theory, is to try and show that there should be many minimal surfaces which algebraically, I should have said algebraically, intersect these long edges once. So the minimal surfaces should be not too far apart, and then sort of conversely, so a bundle is a special case. If you have a long bundle, there should be many minimal surfaces in it, okay, which are copies of the leaf. And Joel is going to talk about this problem as well in the context of, is there a hyperbolic metric for which all the leaves are minimal? That's another interesting question. Okay, and so conversely, one might hope that if you have a collection of minimal surfaces that you can see this bounded geometry picture, that there may be a sort of a way of translating it into minimal surface theory. This is a very vague idea. Okay, so now to get on to the second topic, which is short geodesics. So what I'd like to do is sketch a process. It's a very indirect process to build barriers in hyperbolic manifolds using short geodesics. So a problem about this is there isn't a natural barrier to do. This is a sort of a rather indirect process. Yeah, so let me just go through it and sort of try and explain what the basic idea is. And so what the idea is to produce multiple minimal surfaces in the same isotopy class and to introduce minimal surfaces with different topologies, so they're neither essential nor Heegard. Okay, so it's sort of well known that if you have a short geodesic in a hyperbolic manifold, you have a very big tube about it, so a tube of large diameter. Okay, and a lot is known about the geometry of these tubes. So a very simple process that you can do, which is a little bit like this process here, is you can remove a much smaller tube inside the big tube, and then you have a large collar around the boundary. And you can smooth the metric near the boundary to produce a mean convex boundary. So we want that so that we can do minimization arguments inside the manifold. Okay. Okay, so how are we going to proceed is that what we can do is try and look at the limit of this process. So what we're going to want is tubes which are getting bigger and bigger, and in fact we want to see what happens in the limit, which is as well known. We get convergence to the complete metric on the manifold obtained by removing the loop. So let's have a look at how that works. Okay, so what I want to think about is this situation of a Heegard splitting. So the first game is to try and produce a stable minimal surface in the isotopy class of a Heegard splitting. I mean, when one uses a min-max argument, you get unstable minimal surfaces. That's the natural way of producing Heegard splittings. But what we'd like to do is produce stable ones. So what that will mean is instead of having a single minimax surface, that you get a pair of minimax surfaces with a stable one between them. So this is the sort of game. Okay, but what we're going to do is produce a three-manifold which we don't exactly know what it looks like. So it's just going to be a limiting argument to prove the existence of such three manifolds. But unfortunately, it's a non-explicit argument. Okay, so what the idea is that we look at a handle body and we produce we put a curve. So we choose a complicated curve on the surface. So it's not a very complicated curve, but a curve which winds around a lot and has the property that it meets all the compressing disks, so-called disk-busting curve. Okay, so it's well known that there are a lot of disk-busting curves on the boundary of a handle body. And then what we're going to do is take that curve and push it a little bit into the handle body. And then we're going to do longitudinal Dane surgery. So what that means is that we remove a small tube around the solid torus, around that curve. So we remove small solid torus, and then we're going to glue in a meridian disk. And so what this meridian disk is going to look like is that it's going to run around like this. So it runs around the longitude and only once around the meridional direction, which is where the meridian curve was. So what the idea is that the longitude of this solid torus doesn't change. And in particular, what's happening is that the handle body decomposition remains a handle body decomposition. Okay, so this is sort of really the key idea, that what's going on is that the Heegard splitting becomes a Heegard splitting of the new manifold. Okay, so this is the process. Okay, so we've got a new three-manifold obtained in this way, and we know that geometrically what's happening as this curve winds more and more times around, that we're getting a shorter and shorter geodesic at the centre of this solid torus. Okay, so we're going to get a very short geodesic loop in our hyperbolic three-manifolds. So we've really got a sequence of three-manifolds. There isn't single three-manifold any longer. And what we're going to do is choose a different disk-busting curve in the other handle body and do similarly longitudinal Dane surgery there. So there's actually a pair of short geodesics in each handle body. So this is really what the idea is. Okay, so because these curves are disk busting, if we look at the Heegard splitting, if we remove the curve, there's no compressing disk which misses this curve. It's just the definition of the curve. So what we have is the surface on either with these curves on either side. And if we remove the curves, then the surface becomes essential. So we know by Mix, Simon, Yao, or Shane and Yao that we can isotope sigma to be a least area surface. However, there's a problem, which is that we have to smooth the metric to do this. We need a nice boundary, a mean convex boundary, so we've messed up our hyperbolic metric. So what we would like to do is prove that one of these least area surfaces actually lives outside the collar where we've done the smoothing. So what we're going to do is use a technique of Brian White. So Brian has a very beautiful paper where he describes the space of minimal surfaces or minimal submanifolds as you vary the metric on a manifold. And that's exactly what we're doing here. We're varying the metric on the manifold with these two geodesics removed, or these two short loops removed. So we have a family of metrics on the same manifold, and these metrics are converging to the complete metric, suitably truncated. Okay, so what we can do therefore is look at a least area surface in the complete limit. So if we do that, we can figure out what that surface looks like. We have more control in that situation because there's a fairly straightforward area comparison argument in terms of the genus of the surface, which says how far does the surface actually go into the cusp. So the surface can't go all the way out to infinity. It actually lives in a region in the cusp. And in terms of the cusp geometry and the genus of the surface, you can say how far the surface actually penetrates. So we know that, but then we can use White's argument to say that because the minimal surfaces form a nice actual Banach manifold in the product of the manifold and all these Riemannian metrics, the minimal surface varies smoothly as we vary the metric. But these Dane fillings converge to this complete thing. So what that says is that somewhere far out in the sequence, we must have minimal surfaces which are close to the one in the complete metric. And therefore, these ones will not be in the part of the collar where we've done the smoothing. Okay, so this is sort of a rather indirect argument to prove that there is a least area surface away from the smoothing, and therefore, you know, we can complete that particular hyperbolic metric to one of these Dane-filled ones. Okay, so apologise, this is sort of using a lot of technology to get this result, but I just wanted to sort of give you the basic flavour of the argument of what's required here. Okay, and so then we get one of this, well, in fact, infinitely many of this sequence of Dane fillings, but sufficiently far out, we have these least area minimal surfaces isotopic to our Heegard splittings. Okay, and of course, now we've done that, we can do a minimax argument on either side and get an unstable minimal surface. So we now have three minimal surfaces isotopic to our Heegard splitting. Okay, so this is the basic idea, and of course, you can, once this construction has got going, you can add more and more tubes, which of course is going to give you a more and more complicated three-manifold and a more complicated Heegard splitting. In fact, what's happening is that the manifold, the diameter of the manifold is increasing. So this is becoming longer and longer, even though the Heegard genus is the same, and we're getting these parallel minimal surfaces. So this is sort of in the spirit of the Brock, Minsky, Namazi, Souto model. So this is, but I really feel there should be a better way of doing this. There's not a very explicit argument. There should be a way of doing it so that you really have estimates on these constructions. So you can actually say for a particular hyperbolic three-manifold, you can do this. Okay, so just to quickly finish this discussion, once we can do this, we can also construct surfaces which are neither Heegard nor essential by just starting with a surface which splits the manifold into two regions where at least one of the regions is not a handle body, but there are compressing disks for the surface. So therefore it's neither essential nor Heegard surface. And then you can do exactly the same sort of argument. You can push off disk busting curves, do longitudinal Dane filling, and end up with a new three manifolds and a new surface which is neither essential nor Heegard, and its least area. Okay, so this gives us more examples. So I guess the moral of this is that we can't really, the hyperbolic geometry, particularly these limiting arguments, seem extremely useful for building new sorts of examples of minimal surfaces, but it's really difficult to know what's a conjectural picture for what we should be trying to prove here. So I think this sort of raises a lot of questions. Okay, so that sort of finishes that discussion. So going to be a little bit greedy here and talk about one of my obsessions, which is discrete methods. So there's a sort of really nice discrete version of minimal surfaces called normal surfaces, which some of the people in the audience will know about. So, but for the others, I want to just give a very, very quick sort of 5 or 10 minute introduction to this, and then mention a result which I've sort of been working on for a number of years. And I finally finished off with a really terrific master's student who's gone off to be a banker. But you know, it sort of indicates a very interesting possible connection, I think, between minimal surfaces and normal surfaces. So I just wanted, and again, it throws up a lot of interesting questions. Okay, so just to sort of give you the background to the story, or one version of the story, as Thurston described a beautiful way of looking at hyperbolic structures on three manifolds with tori boundary. These are these complete finite volume, non-compact three manifolds, by looking at ideal triangulations. So the idea is that in hyperbolic geometry, we can look at ideal tetrahedra. So let me sort of draw an ideal tetrahedron. So if we use the upper half space model, we can take 3 points on the plane, which is part of the sphere at infinity, and put our extra vertex at infinity. And so we can think of this Euclidean triangle in the horizontal plane, think of the infinite chimney above it, and then intersect it by looking at a plane through these 3 points, which is in fact going to be a sphere. You know, so we just choose the center point of this triangle, and then take the sphere through it and intersect the chimney with that. You get this beautiful ideal tetrahedron. And what Thurston pointed out, which is a wonderful concrete way of seeing hyperbolic structures, is if you take a bunch of these ideal simplices in hyperbolic space and glue them together so that the faces are glued isometrically, you can really see the hyperbolic geometry in a very interesting way. So there's a wonderful piece of software called Snappy, and there's various other versions of it, originally developed by Jeff Weeks, which you just put in your favorite 3-manifold, and it will produce a hyperbolic triangulation for it. So it's a sort of a marvelous computational tool. So Thurston looked at complex shape parameters. So the idea is that you can move the vertices around so that 2 of the vertices are at 0, 1, and the third vertex is at some complex point Z or Z, depending on which country you come from. And what you can do is then glue them together in terms of polynomial equations in terms of these variables Z. Okay, and so then you get these famous gluing equations of Thurston, and that's what Jeff Week's program solves. But if we linearize these equations, we get a much simpler system called the angle equations, which were studied first by Andrew Casson and Igor Rivett. Okay, so let me just quickly tell you about angle equations, because they give you a sort of a linear theory, which is very helpful, much nicer to solve. So in these ideal hyperbolic simplices, we have a very nice condition, which is that the angle between the faces, if we look at these 3 vertical faces over this Euclidean triangle, we have 3 angles, alpha, beta, and gamma, which add up to pi, but then the opposite angles are equal. So the angles between this sphere and these vertical planes are also alpha, beta, and gamma. So we have this beautiful symmetry for any hyperbolic tetrahedron. And so we can think of these angles as parametrizing our simplex. So we only need 2 angles because alpha plus beta plus gamma is pi. So then the angle equations just say that when you glue the simplices together, the sum of the angles around each edge is 2 pi. It's an obvious condition. And so the space of non-negative solutions is just some affine space of angles, and these are called angle structures. And so these, if the angles are all strictly positive, these are really nice approximations somehow to a hyperbolic structure. So they're very interesting things to look at. So what I want to do is relate these to normal surfaces, which are these sort of discrete analogues of minimal surfaces. So this idea goes back to the 1920s, to Knaser, and then it was developed in the late 1950s by Harkin. So the idea is if we have a simplex and we want to slice it with a plane, obviously in Euclidean geometry, and the same thing works in hyperbolic geometry, if we slice it, we could either cut off a vertex and get a triangular disk, or we could slice between 2 opposite edges, in which case we get a quadrilateral. So we have these elementary topological disks inside a simplex. Obviously, we could draw a much more complicated surface inside a tetrahedron, but the point of view of Harkin and Knaser is that these are very natural disks to study, and a normal surface is one which is gotten by combining a whole bunch of these triangles and quadrilaterals, gluing them together. Okay, and so this is the idea that we're going to do, is that we match these up by, for example, if we want to glue this face to this one, we might have quadrilateral here and a triangle there. We might have 2 quadrilaterals here. And so we glue these 2 arcs to these 2, and we start forming a surface by gluing all the faces up. So these matching equations are obviously linear equations as well, and so we get a space of normal surfaces, which is also a nice affine space. And it turns out these are dual spaces. There's a duality. The coefficients of the angle equations are related to the solutions of the normal surface equations, which is an extremely interesting fact. Okay, so getting on now to a very concrete example, a famous example of Thurston. Thurston observed that the figure 8 knot space, it's the simplest hyperbolic knot. It can be obtained by gluing two ideal tetrahedra together. Sort of an amazing fact. And these ideal tetrahedra, the natural hyperbolic geometry happens to be regular. So these are the most symmetric ideal simplices. So they've got the property that all the dihedral angles are 60 degrees. So the geometry at infinity is of an equilateral triangle. So these are chimneys over equilateral triangles. Okay, Alan Reed, who's in the audience here, described many immersed, totally geodesic surfaces, which are obviously minimal surfaces in this space. So these come from the fact that the coefficients of the gluing, well, the representation of the fundamental group into PSL2C, the isometries, the coefficients of the matrices live in an algebraic number field, so there are many symmetries of that, nice properties, and so you get these many totally geodesic surfaces. So this is a rather unusual situation, but it gives you many essential surfaces. These are also essential. Although they're immersed, they do lift to embeddings in finite sheeted covering. So this gives very many embedded surfaces in hyperbolic three-manifolds. Now, more recently, there's been very spectacular developments related to this sort of idea in the following way. Thurston, a long time ago, had conjectured that hyperbolic three-manifolds don't have totally geodesic surfaces in general, but they should have surfaces of small principal curvature. So you just deform a small amount from totally geodesic. And then Kahn and Markovich proved that this was true. So this is a fantastic breakthrough. All hyperbolic three-manifolds have loads of surfaces of small principal curvature, although I don't believe their argument gives you a good way of actually seeing what these things look like. They just prove they exist, as it were. And Ben Andrews, although this hasn't been published, but he's talked about this, it gave a wonderful flow that proves that all the Kahn-Markovich surfaces actually can be represented by unique minimal surfaces. So there are minimal surfaces also with small principal curvature in the same homotopy class, or there's a unique one in each such homotopy class. So this shows that there are lots of interesting essential minimal surfaces in every hyperbolic three-manifold. How do we see them? Where are they? So this is what I want to describe as the last thing, is a very simple-minded idea for at least starting to do this. So the idea is that we want to play this normal surface game, and the question is, how do we try and arrange a normal surface to look like a surface which has small principal curvature? So this is the guess. Okay, so it's hard to explain, but this is the guess. And I spoke to Thurston about this about 20 years ago, and he immediately produced an example on his computer of a normal surface of this sort. Sort of pretty amazing. And in fact, if I've got time, I might draw it for you. Okay, so the final thing is that with this master student, what we've been able to do, that in the figure 8 knot, we've been able to produce a huge number of normal surfaces which are essential. And we believe they have small principal curvature. We also believe possibly all the Reed examples are of this type, but we haven't proved that. It seems sort of likely. And you can enumerate them, so you can actually list these surfaces, so that's sort of very helpful. Okay, so let me just quickly say what our main result is. And this actually extends beyond the figure 8 knot. So really what you need is an angle structure. That's why I wanted to talk about angle structures. So the two conditions which are really vital are that, first of all, we don't want a normal surface like this. This glues a quadrilateral to a quadrilateral along an edge. And the reason why this is bad is that if you start gluing the quadrilaterals around in a cycle, what you end up with is a tube around an edge, and it's easy to see that you must have large principal curvature. So you're not going to get an essential surface of small principal curvature out that way. Okay, so we need quadrilateral discs which are only glued to triangular discs, and we also want the quadrilateral discs opposite angles which are not too big. And in fact, the not too big turns out to be 60 degrees, which is exactly the answer in the figure 8 knot. Okay, and then it turns out that these normal surfaces are essential. Okay, so let me, maybe I'll draw Thurston's surface because it's so beautiful. I think so. I think I've just got time, and then I'll talk about two problems to finish. Okay, so this is the surface, and the way Thurston did it is that actually he produced a totally geodesic surface, and then he observed that the way the totally geodesic surface sliced through the tetrahedra was like this. So it's so the idea is that what I'm going to do is draw the universal cover. So it's going to be a tessellation of the plane by triangles and quadrilaterals. So I'll just draw enough, and then of course you just repeat. Okay, so it has this beautiful fourfold symmetry. It's got all the right properties to live in the figure 8 knot space. So notice quadrilaterals are not adjacent to quadrilaterals. Around each vertex there's 6 discs, which there must be because the degree of an edge is 6. The dihedral angles are all 60 degrees. So you need 6 tiles around every vertex. And the other condition that you need for a normal surface is you need an even number of quadrilaterals at each vertex. Otherwise, the matching equations don't work. And so this satisfies all of those conditions, and it's not difficult to show that you can immerse this surface into the figure 8 knot space. And in fact, Thurston showed by drawing it on the computer that it is in fact totally geodesic. So it's a wonderful example. Okay, so the first question is, can we build sort of very interesting, explicit minimal surfaces in special classes of hyperbolic 3-manifold? So the game would be, of course, the figure 8 knot, because of this regular structure, it's related to a Coxeter group. Comes from a subgroup of a reflection group. And so it has got all this nice structure, so that aids in finding examples. So, but there are many, there's a very rich theory of such 3-manifolds, and it seems like a good plan to look at these examples to try and build minimal surfaces in there. And sort of related to that is, so there are good constructions of minimal surfaces in both Euclidean geometry, spherical geometry, by looking at disks and reflecting them or doing other operations. And so the idea would be, can you look at these disks rubbed off for normal surfaces, these triangular quadrilateral disks, make them minimal with nice boundary properties in such a way that when you glue them together to form a normal surface, you could actually form a minimal surface at the same time. Okay, so that's the end of my talk. Thank you very much.